All right, folks, we're going to talk about inverse functions today. Just like normal, we're going to start with some group work in class. So what I'm going to have you do is work on problems that are on your front page there. And we will go over with some notes after you're done. Pause the video and take care of that for me, please. Okay, these ones are pretty straightforward. As long as we understand which variable to substitute in for. Okay, this is our calories, so it has to go in for K. And then the other way, starting on part C, because we had filled out this table already for finding the different weights, we can look backwards. The 15.2 was in the table, and it corresponds to 1,000. If you did solve that one by hand, it may have rounded to 1,001 instead, just as a heads up. That is what you were asked to do on 2 and 3. So solve by hand, just getting K by itself. If you struggled with this because of the weird power, I want to kind of remind you of how this works with something you are more familiar with. Okay, so when we think about y equals x squared, if we were trying to solve this for x instead of y, we normally would take the square root on both sides. Okay, but that's not the only option, because when we talk about the square root of x, it's really x to the first power underneath, and it's the square root. So our index right there is a 2. And we can rewrite this as an exponent, as power over root 1/2. And when we raise to the power of the reciprocal, our exponent rule is to multiply. So that says x to the first now. And on this side, it's y to the 1/2, but the x to the first cancels those out to get x by itself like we wanted to. Same thing applies on these ones. You just raise to the reciprocal power anytime we've got that fraction exponent. Okay, and then this generalized as we take whatever our weight is to the 3/4 power, because that's what happened over here, and then we ended up multiplying that 130 over. I put it in the front because generally that's where they show up in front of our variables when we talk about equations. Okay, this one just substitute back in to check, but the idea is to talk about this function right here. On number 4, this is the inverse function. Okay, and it's the inverse function because it undoes the original function. Okay, the operations you see are inverse operations, things that cancel each other out, like multiplication and division, squared and square roots, and so on. And what we're going to do on the back side is just practice finding the inverse function if it exists. Now, I've been using the word function quite a bit here. Okay, the first thing we want to do is decide whether the inverse of the original function would also be a function. So we know an absolute value, and I do want you to sketch this. Okay, we know an absolute value looks like a v. This plus 3 goes to the left. Okay. Here, this is a function because it passes the VLT. When we talk about an inverse, we take the x and the y values of an ordered pair and we trade places, so that it would go to yx. So this point itself, -3, 0, would go to 0, -3. It would be down here instead. But that's not the only thing that happens with an inverse. Okay, since all of them change, there's actually this reflection that's happening over the line y equals x, and I won't need you to draw this on all of them. I just want to talk about it for this very first one. And when we do this, we've got this point, we said 0, -3, and then this reflects here, and this one reflects this way. And so we've got this inverse that isn't a function. We can find it. Okay, we can flip around the ordered pairs, we can reflect it if we have a graph, but we only care about if the inverse is going to be a function. So what we're going to do, instead of drawing out the second function, what we're going to do instead of the VLT on the original, A vertical line test is like an x equals equation. What we're going to do is check out the horizontal line test, a y equals, because that's going to correspond to the vertical line on the inverse. So if a graph passes the HLT, then the inverse will be a function. But if it fails the HLT, then the inverse is not a function. And we're not going to worry about finding it. Okay? So let's go back to the process here. What I want you to do on all of these is step 1, you're just going to graph. And that's a little step 1. Graph the original. Then step 2 is you're going to ask yourself if this passes the HLT. Okay, if you say yes, then you'll continue on to find the inverse. But on ours, this is a no. So what we're going to write is f of x, that's the original equation, fails the HLT. So the inverse is not a function. And that's it. Okay, let's do that same thing for the next one. Okay, your purple note card with sketching these is going to make your life a lot easier. Okay, we know that the parent function of a square root starts at an endpoint and goes to the right. This minus 4 shifts it over to the right of 4. So that endpoint is at 4, 0. First step after that is just testing the HLT on it. This one passes. Okay, so when it passes, you've got another step. You're going to find the domain and the range of the original. Okay, and I'll talk about why we're doing that here in just a minute. You'll see it on this example exactly. Okay, so domain of this is from 4 on. Remember, these are going to be brackets always. And then the range is 0 on. And now we're going to go through the steps that should be familiar from Algebra 2. We're going to find the inverse by first changing f of x to y. Okay, so this is step 2. Because in order for us to switch the x and y places, I have to see a y actually show up in the equation. Okay, so it's lame but important. Then step 3, we actually switch those things. So that would be x equals, and then y minus 4. And now, in the same step, we're going to solve. Okay? So we're trying to get this y by itself, because that's what equations generally look like. We'll have to square both sides. I'm using grouping symbols over here because there is a possibility that there is something inside there that we'd have to write out. In this case, it doesn't apply. Okay? And then I do want to point out that I'm not putting a plus or minus here. I had a square root to start with and going the other way. When we're taking the square root going that way, we have a plus or minus. It doesn't apply when we're going this way. We're just solving for y. Okay, so that's y equals x squared, adding the 4 plus 4. So we've got this quadratic equation. And I hope that makes sense to you because this was a square root, and the inverse operation of that is squared. Okay, but step 4, we're going to rewrite it with function notation. So your inverse notation looks like this -1 power. So it's the inverse of f of x is x squared plus 4. Okay, but not all of it. Okay, not all of it. What you want to include in this is the domain and range of this function. Because kind of like what we did before, again, you don't have to draw this, but it's a visual that's kind of important for this one versus some of the other ones we're going to be doing. When we talk about, excuse me, when we talk about the relationship over y equals x here, this is only half a parabola. So this 4, 0 would go to 0, 4, and this loop would kind of look like this half of the parabola. It's not the whole thing. We know x squared plus 4, okay, goes up 4. So there's the whole thing, but we only want this piece of it. Okay, this piece of it is 0 on and 4 on, but that comes from just taking what we see up here and switching places. Because we're switching the x and the y, the domain and the range just switch. So 0 to infinity becomes the domain, and 4 to infinity becomes the range, and we can see that visual here. Okay, so the inverse of a square root is not a parabola, it's half of one. Okay, it has to be restricted because the other half of the parabola doesn't exist on this version. Okay. All right, so step 1, you're going to sketch, do the HLT. Okay, if no, fails and inverse is not a function. If yes, domain and range. Step 2 of 3, you're finding your inverse, and step 4, you're doing some final notation with the new domain and range. Okay, so we're going to do this again for this one. Okay, so x squared minus 4. Sketching it first, x squared, parabola starts at 0, 0. Remember, parentheses are there when you don't see them. So this goes down 4. And then when we do the HLT on this, we do not have a inverse that's going to be a function, because when we flip it, it would fail the VLT. So this one we don't need domain and range because we're not going to flip it. We're just going to say that f of x fails the HLT. So the inverse is not a function. Okay, it exists. We could find it. We're just not going to. Okay. This next one, parent function, is a little bit more fun. We've got parent function of 1 over x here. This 4 is a vertical stretch. This plus 3 means going to the left 3. So remember, for this one, the translations are going to tell us where our asymptotes have gone. They start at 0, 0, and this plus 3 goes to the left. So now we have one at x equals negative 3. And I do want you to put these on your graph. We don't have a plus or minus to the side here, so our second one is still at y equals 0. Okay. And then we're doing a stretched out hyperbola. Okay, the stretch doesn't super matter because the purpose of this sketch is to talk about whether it passes the HLT. Okay, in the case of this rational function, okay, this hyperbola, we would say yes, it does pass the HLT, which means we're going to find the domain and range. Domain is everything except for negative 3, so we write negative infinity to negative 3, union, negative 3 on. And then same process with the range, but it stops at 0 instead. Okay, that was step 1. Step 2, we're going to change that f of x to y. Because we decided the inverse was going to be a function, we're going to find it. In order to find the inverse function, we have to switch the x into y. So x equals 4 over y plus 3. Now in this stage, you're allowed to skip as many steps as you want. Okay, you're going to solve for y in however long it takes you. Okay, and I'm actually going to let you try this before I show you how I would do it. Okay, so I want you to pause the video and try to get y by itself here. Okay. In the case of these problems, many of you, I'm sure, did the y plus 3 because we're used to, when we see something in the denominator, we multiply it across. That's not wrong, okay? But at this point, I want to talk about what to do next, okay? We have the option of distributing through or moving this times x to the other side. And that's really probably the better idea here, is moving it. That way we don't have to worry about too many steps when we distribute it, only to get y by itself again. Because as soon as we distribute it, we're adding a variable to y that we then have to get rid of later. Okay? So if we do this, then we have y plus 3 equals 4 over x, and we just have to subtract that over. Now, I do want to show you one more thing that's going to make your life a little bit easier here. Okay, this original equation, and when we actually got the y out of the denominator and moved over the x, you'll notice that these two things just switch places because we multiplied this one over and we divided that one back. Okay, so I'm usually going to skip these extra steps with the work because I know that pattern is going to happen every single time. Okay, multiply the bottom over so it goes there, and then that x goes to the denominator. Okay, so that's something, if you recognize it, you can absolutely use. Step 4, we're going to write our function notation. Okay, inverse of f of x uses this -1 power. And then 4 over x minus 3. Okay, if you think about the graph at this one from the parent function, okay, we have no translation left and right, so that would be an asymptote at 0, x equals 0. And this means an asymptote has gone down to -3, which is exactly what our domain and range switches around to. Okay, so we work hard on the original graph so that we don't have to work hard on the inverse. Okay, you just take the domain from the original and move it to the range. And the range from the original, like this one, becomes the new domain. But it should match the equation that you come up with. Last thing we're going to do is talk about composites with inverses. Okay, the first example here is just a composite to refresh our memory on those before we get to how they're used to prove if two functions are inverses of each other. Okay, it's another method. So here on this one, it wanted f first. Okay, so remember you start with the f function, but you leave some extra space where x is because that's where you're going to plug in the other part. So our other part is this square root symbol, x minus 7. Okay, and in this case, the square and the square root cancel out, so you've got x minus 7 and then plus 1. So our final function, and I do want you to rename it for me, is f of g of x is x minus 6, which actually looks like a line, okay? But when we talk about its domain, remember, domains of composites, we have to think about the domain and the range of the original equation, because this is really the function. We had just simplified it. Okay, so this is what we're looking at when we talk about restrictions. Going back to the original, this first one's a parabola, which means the domain is all real numbers. No problems. Remember, problems show up with fractions and roots. Okay, we do have a root here. Graph of this one, right 7, means our domain is from 7 to infinity. Okay, always pay attention if we have a reflection over the y. If there's a negative in front of x, it'll go the other way and start at negative infinity. Okay? But because of this restriction right here, remember we have to use the most restrictive domain. So we have to use that. We can see it here. If we plugged in like a 6, 6 minus 7 would cause problems because we can't take the square root of that negative value. Okay? With that in mind, our domain is 7 to infinity. Okay? If you want a graph to check this, you're not going to be able to graph this version. Okay, this is the version before you simplify is what you'd want to graph in order to see this restricted domain actually show up. Okay? Same thing on the other one. We're going to start with g, this function, but where we see x, we're going to leave some space. Okay, so in here, we're going to plug in the other function, but then minus 7. Inside, we put this x squared plus 1. Okay, in this case, the parentheses don't matter because we're just subtracting 7. It's just one term. So we can simplify by x squared minus 6, and then go ahead and write our function here. Okay. So now we're going to talk about this domain here. Again, our most restrictive domain to start with is 7 to infinity, but this actually kind of changes some things here. When we're dealing with composites, what we haven't really talked about much is where we're thinking. It's really the inverse or the inside function that gives us the most restrictive domain. In this case, that thing we plugged in g was the most restricted part. In this case, when we plugged it in, there wasn't any restrictions with x squared plus 1, so there's no problem with that part. Okay, but because we have a root here, there is a potential for problem on the entire thing. Okay, but this is actually a graph that is special. It's not like our regular square root. There's a squared underneath. Okay, so if we think about a number line, a lot of times we do negative, 0, and positive. If I plug in a negative number and square it, I get positive, but minus 6 could potentially make it negative. So we do have some restrictions here as well. We're going to do the same thing we did on this one way back when we first started talking about translations, and you can always find the endpoint by setting that thing equal to 0. So for this one, we're going to do the same thing. X squared minus 6 equals 0, and then x squared equals 6. Take the square root here, and we've got x equals this plus or minus thing I was talking about earlier is important, the square root of 6. So this graph, okay, can have actually 2 endpoints. So we're going to take a minute to take a look at it, just so you get comfortable using your graph when you have weird things show up. Okay, I don't expect you always to do this algebraically. I want you to use that in combination with the use of your graph. Okay, so typing this in, we've got an x squared minus 6. And then I'm just going to do a zoom 6 because I know my window's weird. Okay, we've got 2 endpoints here, and they represent the positive and the negative square root of 6. And you wouldn't have been able to see that without algebra. We can see the graph is strange, but you wouldn't have been able to find those numbers on your calculator because even though they're minimums, you can't do a left bound, right bound, and it's an irrational number that you're not going to be able to find exactly on there. Okay, so the domain of this thing is actually negative infinity to the negative square root of 6, and then it doesn't start at negative square root of 6. It starts at the positive one. Okay, and do a little sketch of that so you know where that came from. Okay. We're going to graph, if we're graphing, the plugged-in version. In this case, our plugged-in version didn't have any restrictions, so the simplified was fine. If you want to be extra safe, plug in that original value, and it's going to give you that same idea. Okay. All right. This one here is where we're actually going to use determining whether inverses are functions. Okay, I'm going to have you flip back over to the front side because this we actually already talked about, just not formalized. Okay, when we plug in the number of calories you get into the original equation and see if the weight matches, what we're really saying is we're checking if f of g of x, okay, is equal to x. Okay, in this case, we are plugging in the number of calories we got, so we were plugging in k, and we're seeing if we got, in the original equation, we see if the weight matches. Okay, so our first function, we're taking the number of calories into the first function, and then we're seeing if that actually matches. Basically, you're taking this and going in the reverse order. It's just a double check. So what we're going to do on here to prove whether or not these are functions is that exact thing. Now I use the f of g of x notation intentionally because that's what I'm going to give you here. So what I want you to do up here is write a little note. If functions are inverses, then f of g of x will equal x, but so will g of f of x. So we're going to check both. And as soon as one of them is something other than x, then we can stop. We're very obviously clear that these things are not inverses. Okay, but I'm going to have you do both to show that they really are true either direction that we do it. Okay, so starting now, f of g of x, and you do have to label this for me, says we start with the f function, but we're going to leave space here. Okay, that space is where we put the 2x minus 4, and then we simplify. So that says x minus 2 plus 2, and sure enough, that does equal x. So far so good. Now we're going to do g of f of x, and hope the same thing happens. Okay, this time I'm starting with the g function, so I'm starting with 2, leaving some space, minus 4. And inside this one, I'm putting the 1/2 x plus 2. Distributing through, I've got x plus 1 minus 4. Sorry, x plus 4 minus 4. And then cancel out again. So both of these equal to x, and that's what we wanted to. So I'll have you write this similar to what we did with even and odd. We'll just write a statement that happened. F of g of x was equal to g of f of x. Okay, they matched, but also they were both equal to x. That's what makes our functions inverses. Spelling off there. Okay? If one of those things is not true, either this is not equal or the first one does not simplify to x, we're done. And we say that they're not inverses. Okay? So let's check out the next one. F of g of x. Okay, starting with the f function, leaving some space. Inside, we're writing 1/3 x minus 6 and simplifying. So this says x minus 18 plus 9, and that is not equal to x. This simplifies to x minus 9, and as soon as it's not equal to x, you say that. F of g of x was not equal to x, therefore not inverses. Has to be x itself. Otherwise, this is like plugging in the value we got into the original and not getting the same thing. Okay, not getting that weight that we determined it was supposed to be. Okay, I want you to pause the video and try number 8 for me. There are a lot of fractions involved, so if you get stuck, I'll walk you through it. Okay, but I want you to try it first on your own. Okay, the parentheses really matter here. So when we're talking about f of g of x, just like I did over here, it might be helpful for you to put those parentheses in there, because I'm starting with 3, but in these parentheses is where the other function goes, and that's 3 over x. Okay? And dividing by 3 over x is the same thing as multiplying by x over 3. This is gone. Okay? And then that says 3x over 3, or x. Okay? Going the other way, we want to check if it works as well. And in the case of these ones, when they look exactly the same when you plug them in, you don't have to show all the extra work, because check it out. This also says 3 over x, which we just saw up here equals x. Okay? For the first one, you must show the work. I need you to know that you know how to simplify a fraction inside of a fraction. Okay, so write that out for me. Okay, and I do want to emphasize, because a lot of times you're not always explained why things work the way they work. So when we're talking about 1 over 1/2 and we're simplifying it, you were taught to multiply by the reciprocal. But what you're actually doing is multiplying by the reciprocal over itself, okay, top and bottom, because this is multiplying by 1. And when you multiply by 1, we've talked about this, it doesn't change the value. What happens, though, is the top part gets multiplied by the reciprocal, and the bottom part cancels out to 1, which is why we just cross that out, and we don't write the second part, because we know it cancels out. Okay, we're not changing the value by doing this, because we're really doing it on top and bottom. You just probably weren't shown that. Okay, so we've got equal x, so we're going to write it, f of g of x and g of f of x, both equal x, therefore inverses. Okay. Homework's over a lot of similar stuff. You will see a ton of review since this is the last day of the chapter. Please let me know if you have any questions, and be sure to be checking your answers.